For 6.2, we're going to get into multiplying and dividing radical expressions and back into simplifying radical expressions. And those radical expressions, again, when simplified, we have certain rules. When we simplified radicals earlier in Algebra 2, we had a problem like, let's say, the square root of 98. And I ask you to simplify that. We simply don't pick a calculator up and simplify it. We've got to find a perfect square factor of 48 or of 98, which would be the square root of 49 and the square root of 2. And then I could rewrite square root of 49 as 7, square root of 2. Well, now with dealing with these larger roots, we're going to be dealing with cubed roots and fourth roots and fifth roots. So this is kind of for your reference. This is saying that if you have 2 to the second power, it equals 4, 2 to the third power equals 8, 2 to the fourth power equals 16, 2 to the fifth power equals 32, 2 to the sixth power equals 64. Well, just like that, if I did the sixth root of 64, it would equal 2. If I did the fifth root of 243, it would equal 3. So this kind of gives you a reference sheet for perfect squares, perfect cubes, perfect fourth roots, perfect fifth roots, perfect sixth roots. And again, you just look at this number, and if I were to take the fifth root of this number, it would equal 7. Okay, so as we go through that, this is a very good reference sheet. Again, I'm not going to go through each single one of these, but you can go back and look at this, pause it, and write these down. Definitely for perfect squares, I'd know up to 20. For perfect cubes, up to 10. Perfect fourth powers, up to probably 10. Perfect fifth powers, we don't normally go over 6. But these numbers are very commonly used, and they're used a lot throughout pre-calculus as well. So let's take a look at a few of these examples. And this is just, again, going back to we're allowed to multiply if we have the same index. So I have this problem right here which says cube root of 6 times the square root of 2. I can't physically multiply these two numbers because I don't have the same index. This 6 and this 2 make it so that I can't do this problem. So if I asked you to do this problem, you literally would just rewrite it. And I can't multiply this because I have different indexes. I have to have the same index. So in this problem, you see I have the same index, okay? I can multiply -4 times 2 and make it -8. Now, I ask myself, is there a perfect cube of -8? And because -8 is -2 times -2 times -2, the answer to this is just -2. Again, cube root means you have to have 3 of the same exact number to be able to simplify. So we're going to start off with just simplifying. Simplest form, no nth root factors under the radicand. And to try to make sense of this, I said you could have no perfect squares under the radicand before. Well, now we're going to go into third root, fourth root, fifth roots. So I'm looking for perfect cube roots of 54. So again, I would go back to this list, and I'm looking for perfect cube roots. Are there any of these numbers right here raised to the third power, okay, down this list that equal or are a factor of 54? And when I do that, I could say, oh yes, this is the same exact thing as the cube root of 27 times the cube root of 2, okay? And then now I've got the cube root of 5x's, okay? So there's 2 ways that I'm going to talk about this. I can write them all out. This is what x to the 5th means. This index of 3 means I need a group of 3 to be able to take 1 out. So cube root of 27 is 3. I can take these 3 x's out, and when I take them out, each group of 3 counts as 1 x on the outside. Okay, whatever I can't simplify or take out, I put back underneath as x squared. You can also take the number of x's and divide it by the index. So I've got 5 indexes or 5 x's. I can divide that by x to the third. So this would equal, again, that goes in one time, x, and I'd be left with 2 x's left over when I subtract them. That remainder is what gets thrown back underneath. So this is considered completely simplified. Again, definitely harder because we're looking at larger numbers. So I'm looking at perfect cubes and this 128. So I'm going to go back to this list. Do I have any perfect cubes that are divisible by 128? And if you don't know that, you pick up a calculator and hopefully you realize it's certainly not divisible by 125. Is it divisible by 64? And the answer to that is yes. So I would rewrite this as the cube root of 64, cube root of 2, cube root of x to the 7th, which means I have 7 x's. How many groups of 3 can I make? 1, 2. So I can take 2 x's out. So this simplifies to 4 because the cube root of 64 is 4. I can take 2 x's out. What am I left with underneath that I can't simplify? I can't simplify the 2, and I'm only left with 1x, so I'm left with a 2x underneath. Okay. And again, how am I knowing to look at cube roots? Because of the index. If this was a 4, I would be looking at 4th roots. Okay, so again, product, multiply. So now I'm dealing with square roots here, and I'm just going to straight multiply here. Okay, 720 times 10. I'm sorry, 72 times 10, which equals 720. So index is 2. I've got 720. I combine the x's by adding them. So I've got x to the 4th, y to the 6th. Okay, so 720. Let's go back to that list. Is 720 a perfect square? So I'm looking at perfect squares. No. Is 720 divisible by any of these numbers? Well, I got to get my calculator out and start looking to see if it's divisible by any of these. Okay, and I want to find the largest number first. So again, I could start dividing all of these by 400, by 361 to try and find that. I know for a fact it's divisible by 9. But it'd be 9 and 80. And in 80, I can get a perfect square. So 720 divided by 36. 36 and 20 still can get a perfect square. 720 divided by 144. There we go. So again, I'm going through these list of numbers and seeing what 720 is divisible by. And I chose a couple of numbers that were smaller, but saw that the answer still had a perfect square in it. So I kept going larger and larger. So this simplifies to the square root of 144 square root of 5, and then x to the 4th, and I'm just going to break these up, y to the 6th. Okay, well, this would be 12. X to the 4th means x, 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 x. How many groups of 2 can I make? 1, 2. So I take out an x squared. Y to the 6th is y, 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 y. 1, 2, 3. So I'd have a y to the 3rd, and what am I left with underneath the square root? 5. So this would simplify to 12x squared y cubed square root of 5. How come there's no variables left underneath? Because the index is 2, and when I divide 4 by 2, it comes out evenly. There's no remainder. Okay, so again, same thing with this problem. You have the square root. You can multiply 45 times 35, and it gives you the square root of 1575. Some large numbers here. X to the 6th, y to the 7th. Okay, so I'm trying to find a perfect square factor in 1,575. I'm going to divide it by 25 just to look at it because it gives me a smaller number. When I divide it by 25, it gives me 63. I know 63 is divisible by 9 and 7, and 9's a perfect square. So I've got 5 and 3 as perfect squares. So I'm betting you 1575 is divisible by 15. I'm sorry, the perfect square of 15, which is 225. Yeah, 225. So I want to try and divide this. I'm going to divide this by 225. So 1575 divided by 225, and that equals 7. So again, this breaks down to square root of 225, square root of 7. Again, 6 x's and 7 y's. And you don't need to write it down like this. I'm just showing it to you. Well, this is 25. 6 x's gives me 3 groups of 2, so it'd be x to the 3rd. 7 y's gives me 3 groups of y, so it'd also be y to the 3rd. But notice, there's no more x's left. I still have a y left over. So I'm left with 7y underneath. So this is multiplying the radicals and simplifying them. We're going to look at dividing now. And again, we got to go back to rationalizing the denominator for some of these as well. But division, if I have the same index, I can just simply divide and do the math here. So because 18 and 2 divide and I have the same index, I get 9 underneath the square root. And then how do you divide exponents? You subtract them. So x to the 5th divided by x to the 3rd would be x to the 2nd. And then now to simplify this, I would just get 3x because the square root of 9 is 3, and I need 2 x's to take it out. So that would give me that. Same index, but it's cubed, so I can take 162 and divide it by 3. That would give me the cube root of 54. and I subtract the exponent, so it'll be y to the third. Notice that the larger number is always on top, so I don't have a fraction anymore. I think we already simplified 54, right? We wrote this as the cube root of 27, cube root of 2, and then cube root of 3y's. So I would get 3. How many y's can I take out? Index tells me I need groups of 3, so I can take 1 out, and I'm left with the cube root of 2. So that's how that simplifies when you're dividing. So again, same index, you just simply divide and then simplify. Now, when they get more challenging is when you can't just divide them. So you have to do what's rationalizing the denominator. And this was rationalizing for a perfect square. But now if I had a problem that looked like this, the cube root of 2, I've got to ask myself, how many more 2's do I need? And I would actually have to multiply by the cube root of 4, because this is 2 times 2, right? And I need 3 of them to write it out. So we're going to have to make sure we pay attention to the index. So for this problem right here, the index is 3. So I need 3 of the same number to be able to simplify. So I would multiply top and bottom by the cube root of 12. And I'm going to write it out. Cube root of 12. Okay, where am I getting the 12 and 12 from? Because this is only 112. I need 3 of them. So I'm going to multiply this whole thing by 12 and 12. How many y's do I have on the bottom? I have 2, which means I need 1 more y. So I'm going to multiply by top and bottom by the cube root of y. And how many z's do I need? I have 1. I need 2 more. I'm going to multiply by z squared. Now, this is showing every single step of every number. I wouldn't show 12 and 12. I would show 144. But I'm going to show this just as we do this. So we're going to multiply the top. I've got 5 times 12 times 12. The top can look ugly, and it will. Okay, so on the top, I've got the cube root of 720, x squared. I'm allowed to have an x squared underneath, a y, and a z squared. On the bottom now, the whole reason that I multiplied by 12 by 12 by 12 is so that I can get a perfect cube. So it just eliminates the cube root on the bottom and gives me whatever I multiplied by 3 times. Same thing with the y. I have 2 y's. I multiply by 1 more. That gives me 3 y's. The cube root of y third is just y. And then same thing with the z's. I have 1 z. I multiply by 2 more. It gives me 3. So on the bottom, it's now rationalized. Now I have to look at the top and ask myself, does 720 have a perfect cube in it? Okay, so I go back to 720 and I go back to my perfect cubes, this list right here. So my perfect cube, does 720 divisible by any of these numbers? Okay, and I believe it's divisible by 8 and 8 only of the perfect cubes. Again, we're not looking at this list because the index is 3. So this is divisible here by 8. So I would rewrite the top now as the cube root of 8, cube root of 90, because 8 times 90 is 720, and there's no perfect cube factor of 90. Okay, square root of, or cube root of x squared y z squared. And again, none of these are perfect cubes because I need 3 of them, and it doesn't matter what's on the top. All over 12yz. So now I have 2 cube root of 90 x squared y z squared, and I can have this on the top all over 12yz. Now it's important to note, I can't cancel these 2 y's because this is underneath the radical, everything here. I can simplify the 2 and the 12. So this simplifies to cube root of 90 x squared y z squared, all underneath the radical, over 2 divided by, or simplifying that fraction, the 2 and the 12 gives me a 6 y z. It's really important to know the difference between a variable that's under a radical and a variable that's not. You can't simplify those. So that is rationalizing the denominator.